Hey, it's me, it's your pocket tutor, and in today's lesson we're gonna solve some problems about equilibrium, both in solids and in fluids. The first one says, a spring horizontally placed has an end fixed to the wall and the other end is linked to a brick that weighs 27 newtons. The elastic constant of the spring is K equal to 180 Newton per meter, and the static friction coefficient between the brick and the floor is 0.9. The brick is pulled until the spring is extended by 20 centimeters. And the questions are, which are the modules of the elastic force and of the friction force between the brick and the floor? And if you let go of the brick, will it move? So let's start drawing a picture. A spring is horizontally placed, and an end is fixed to the wall. The other end is linked to a brick. Its weight is 27 newtons, and this can be the floor. The spring constant K is equal to 180 Newton per meter, and the friction coefficient mu is equal to 0.90. The brick is pulled until the spring is elongated by 20 centimeters. This means that this distance is 20 centimeters. And now we need to find all the forces acting on the brick, which are given by its weight, the normal force, the elastic force Fe that is pulling the brick towards the wall, and the friction force. We know that the elastic force is given by the product between the spring constant and the elongation of the spring. This means that Fe will be equal to 180 Newton over meters times 20 centimeters or 0.2 meters, which will be equal to 36 newtons. We already know the value of the weight that is given by 27 newtons. This means that the normal force will be also equal to 27 newtons. Now the friction force is equal to the friction coefficient mu times the normal force, which will be equal to 0.9 times 27 newtons, and this is equal to 24.3 newtons. And this is the maximum value that can have the friction force. And this already answers the first question, since these are the two moduli of the elastic force and of the friction force. For what concerns instead the second question, that is, if we let go of the brick, will it move? Then the answer is yes, because the elastic force that is pulling the brick towards the wall in this direction is greater than the friction force. This means that the friction is not enough to keep the brick in its place, and the elastic force, being greater, will pull the brick towards the wall. The second exercise says, a porter is holding a 33.5 kilograms crate resting on a 2.4 meters high and 10 meters long inclined walkway. What is the value of the balancing force needed to keep the crate in balance, and what are the modules of the pressing force on the inclined plane and the reaction force of the plane? Well, let's draw a picture also here. We have an inclined walkway that its length is equal to 10 meters and its height is 2.4 meters. And then we have a crate, and draw it this way, and a porter that is holding it in such a way. The crate has a mass of 33.5 kilograms. This means that its weight will be equal to the mass times the Earth acceleration constant. And the problem asks, which is the balancing force needed to keep the crate in place? The balancing force will be given by this one. We can call it force balancing. And how to solve this problem? Well, first thing, we have to decompose the weight force of the crate in the two directions, one perpendicular to the inclined plane and one parallel. In order for the crate to be in equilibrium, we need that the parallel force, F parallel, must be equal to the balancing force. And we know that the parallel component of the weight, F parallel, is equal to the weight times the height of the inclined plane divided by its length. This means that will be equal to the mass times g times the height divided by its length. And putting inside the numbers, this is 33.5 kilograms times g, that is 9.81 newtons over kilograms, times the height, 2.4 divided by 10. And this will be equal to 78.9 newtons, which is also the value of the balancing force needed to keep the crate in place. The second question instead asks which are the modules of the pressing force on the inclined plane and the reaction force of the plane, which means that we have to find the modules of F perpendicular and the normal force given by the plane. In a similar way, we can compute the F perpendicular as the total weight times the base length of the inclined plane divided by the total length, where the base length is given by this segment here. And it can be computed with Pythagoras theorem, which means that B will be equal to the square root of 10 to the second power minus 2.4 to the second power. And this one is equal to 9.7 meters. And this means that the perpendicular force will be equal to 33.5 times 9.81 times 9.7 divided by 10, which will be equal to 319 newtons, which is both the modulus of the perpendicular force and also of the reaction force given by the plane, which answers the second question. The third problem says two workers are carrying a crate weighing 1,000 newtons, resting on a 2 meters long rod of negligible weight. The crate is 80 centimeters from one of the two workers. How much are the intensities of the forces that the two workers must apply to be able to support a crate? And also in this case, let's draw a picture. We have a rod of negligible weight and we have a weight of 1,000 newtons. Two workers are holding the weight, and we know that this distance is 80 centimeters. How much are the two different intensities of the forces, which means these two forces here, that we can call F1 and F2, that allow for the crate to be supported? We know that the sum of F1 and F2 must be equal to 1,000 newtons, otherwise it wouldn't be supported. But which are the respective intensities? In order to compute them, we need to calculate their momentum, and in order to do so, we need to identify a single point that acts as our rotation point. And in order to simplify the problem, we can put the point in one of the two locations of the workers. And for simplicity, let's consider this one here, and we can call A. Now we need to compute the momentum of all the forces with respect to A. And we know that the momentum is given by the force times the arm, or the distance between the force and the application point. Since the distance of F2 from A is equal to 0, in this way we exclude the momentum from F2, and this simplifies the problem. So we know that the momentum from the weight itself, so from the crate, will be equal to 1,000 newtons times its distance from the application point, which is 1 meter and 20 centimeters, while the momentum of F1 will be equal to the F1 times its distance, that is 2 meters. Now the momentum given by the crate is equal to 1,200 Newton times meters, while for the second one we don't know its value, but we know that the two momentums must be equal in order for the weight to be in equilibrium. This means that the momentum given by F1 must be equal to 1,200 newtons times meter, but is also equal to F1 times 2. Now from this equation, we can see that F1 is equal to 1,200 newtons per meter divided by 2 meters, which means that F1 will be equal to 600 newtons. And in order to find the value of F2, we could compute all the momentums with respect to a point B, located where is the first worker, and do the same calculations, but we can also compute the difference between the weight and the force applied by the second worker, because we know that along the vertical direction, we need that the sum of all the forces must be equal to 0 in order to have equilibrium. And since we have a downward force of 1,000 newtons given by the weight, and an upward force F1 equal to 600 newtons given by the first worker, the second worker must be applying a force equal to 400 newtons, which means that F2 must be equal to 400 newtons in order for the system to be in equilibrium. And now let's see the last exercise about the equilibrium of solids, which says that a crane has an arm of 25 meters. At the end of the arm, there is a mobile trolley weighing 50 kilograms, to which a load of 340 kilograms is attached. What is the intensity of the weight force of the system formed by the trolley and the load? And what is the moment value of the weight force with respect to the beginning of the arm? Let's draw a crane that we can sketch in this way, doesn't matter. And its arm is 25 meters long. At the end of the arm, there is a mobile trolley, to which is attached a load of 340 kilograms. We can call the mass of the trolley is 50 kilograms, and the mass of the load is 340 kilograms. What is the intensity of the weight force of the system formed by the trolley and the load? We can say that total weight is given by the weight of the trolley plus the weight of the load, which is 50 kilograms times G plus 340 times G, which is equal to 3,826 newtons. Instead, in order to reply to the second question, we just need to apply the equation that says the moment of the force is given by the force itself times the arm with respect to the point that we are considering. In this case, the beginning of the arm, we can call it A, which means that the moment will be equal to 3,825 times 25 meters, which is equal to 95,625 newtons times meters. Now the trolley is moved along the crane until the moment decreases to 72,000 newtons per meter, which means that we are moving the trolley in this direction until a point, here we can call it B, and in this position, in position B, the moment of all the system is equal to 72,000. Since the weight of the system doesn't change, we just need to compute the new arm with respect to which we have a moment of 72,000 Newton per meter, which means that the moment of the system in position B, that is equal to the force times the arm, let's call it A2, because it's in the second position, is equal to 72,000 Newton per meter. Since the force doesn't change, we just need to compute A2, which is equal to 72,000 divided by the total force, which is 3,825, and this results 18.82 meters, which answers the second question. So the new position will be 18.82 meters with respect to the beginning of the arm, in order for the weight to apply a moment of 72,000 Newton per meter. And now let's see some exercises about fluids equilibrium. The first one says, a submarine dives into the sea at a depth of 105 meters. The density of water is 1,030 kilograms over cubic meters. Compute the total pressure to which the internal surface is subjected. In order to solve this problem, we need to recall Stevin's law, which tells us the pressure applied by a liquid. Stevin's law, in fact, says that the pressure is given by G, Earth acceleration constant, times d, the density of the liquid, times the height with respect to which we are computing its pressure. The total pressure will then be given by P equal to P0, meaning the pressure that is already acting on top of the fluid surface, in this case atmospheric pressure, plus G times D times H. Now let's draw a scheme of the problem. We have the water surface, on top of which we have the atmospheric pressure that we can call P0, that is acting on the water level, and then we have a submarine, which is at 105 meters in depth. The atmospheric pressure is almost equal to 10 to the 5th power pascals, and the total pressure to which the submarine is subjected is given by P, that is 10 to the 5, which is P0, times G, 9.81, times density, that is 1030 kilograms over cubic meters, times depth that we are considering, in this case 105 meters. And if we compute this calculation, we'll find that the total pressure is given by 1.16 times 10 to the 6th power pascals. As you can see, it's quite easy, you just have to remember one simple formula. The next exercise about fluids equilibrium says, a cube of an unknown material floats completely immersed in mercury, which has a density D equal 13.6 times 10 to the 3rd kilograms over cubic meters. The length of one side of the cube is 1 centimeter. How much is the mass of the cube? So we have a container which is holding mercury, and then a cube of an unknown material that is floating inside mercury, but completely immersed. If the cube is completely immersed but is floating, we already know the density of the material composing the cube, which is the same of the fluid into which it is immersed. This is because if we have any object and we put it inside a fluid, if it floats, it means that the density of the body is lower than the one of the fluid. Just imagine wood inside water. The density of wood is almost always lower than water, while if the density of the material is higher than the density of the fluid, just imagine a rock that you throw inside a river. It just sinks because its density is higher than the one of water. In this case, since it's completely immersed but still flowing, this means that the densities are exactly the same. And by knowing that this is a cube and the length of one of its sides is 1 centimeter, the volume of the cube will be equal to 1 to the 3rd power centimeters cubed, which is 1 centimeter cubed. And now, since we know the volume, we know the density. Since we said that the density is exactly the same as the one of mercury, we know that the mass will be equal to the volume times the density. In this case, we need to convert the units of measurement, but this is quite simple, since in order to go from kilograms over cubic meters to grams over centimeters cubed, we just need to divide by 1,000. This means that the mass will be given by 1 centimeter cube, which is the volume, times the density, that is 13.6 grams over cubic centimeters. And therefore the mass, M, will be equal to 13.6 grams. The last exercise says, a cylinder of mass 100 grams and a volume of 60.5 cubic centimeters floats in a liquid. Its total height is 9.75 centimeters, and the immersed part has a height of 6.15 centimeters. What is the density of the cylinder and what is the density of the liquid? So we have a cylinder that is floating, but it's not fully immersed, so we don't know its density. And the immersed part is 6.15 centimeters, and its total height is 9.75 centimeters. We know its mass, that is 100 grams, and its volume, that is 60.5 cubic centimeters. In order to solve this problem, we need to recall Archimedes' law, or Archimedes' thrust, which says that when a body is immersed in a fluid, it feels an upward force equal to the weight of the fluid that is being displaced. This means that if we represent all the forces acting on the cylinder, we will have its weight and Archimedes' thrust. Archimedes' thrust is given by G times the density of the fluid times the volume that is immersed, so the volume of the body immersed inside a fluid. In this expression, we don't know Archimedes' thrust and we don't know the density of the fluid. But what we know is that since the cylinder is floating, we can assume it's in equilibrium, and therefore Archimedes' thrust must be equal to the weight of the body. The weight of the body is given by its mass times G, which is 0.1 kilograms times 9.81 Newton over kilograms, and is almost equal to 1 Newton, and which is also equal to Archimedes' thrust. This means that 1 Newton is equal to G times the density of the fluid times the volume of the body that is immersed in the fluid. To find the volume that is immersed, we just need to find the base area A of the cylinder and then compute the volume of the cylinder immersed, since we already know its height. In order to find the area, we can compute A as the total volume of the cylinder divided by the total height of the cylinder, which is equal to 60.5 divided by 9.75, which is equal to 6.2 centimeters square. Now the volume of the immersed part, VI, is just given by the height that is immersed, 6.15 centimeters, times the area, 6.2 squared centimeters, which is equal to 38.13 cubic centimeters. And now, putting this value here, we can find that the density of the fluid or density of the liquid is given by 1 Newton divided by G times the volume that is being immersed. And this is finally equal to 2.7 grams over cubic centimeters, which is the density of the fluid into which the cylinder is immersed. In order to compute the density of the cylinder, we could have done this before, but the density of the cylinder is equal to the ratio between the mass of the cylinder divided by its volume, which is 100 grams divided by 60.5 cubic centimeters, which is equal to 1.65 grams over cubic centimeters. So you see, in the previous exercise, when the two densities are the same, the body is floating but completely immersed. In this case instead, when the two densities are different, so when the density of the body is lower than the density of the fluid, the body floats on top of the surface. And this is it for today for this lesson on exercises about equilibrium. See you next time.